Our life turns round bearings. Invisible, unnoticed, they do an unromantic but essential job. They keep things moving. This organization alone produces 1.25 million of them a day. 1.25 million pieces of precision engineering, all sharing the same object: the elimination of sliding friction. Billions of rolling bearings keep our industry, our transport, and our domestic lives moving by eliminating sliding friction. Elimination of sliding friction. The idea is not new, of course. The supposition is that the Egyptians used rolling elements to move their larger monuments. Primitive rollers were certainly in use a mere 2,500 years ago. Herodotus specifically mentions their use for transport, launching of ships, and military engines. And later, Leonardo da Vinci designed bearings as well as flying machines. He called them wonderful, supernatural pivots in highest perfection. This is possibly the oldest rolling bearing in Britain, a 1780 thrust bearing. It was tailor-made for a specific job. Indeed, bearings were not mass-produced until after bicycles were invented. As these machines increased in popularity, so an increasing number of applications flowed into Her Majesty's Patent Office. 1877, from J.H. Hughes for a cycle bearing with curved track surfaces. 1881, from L.H. Pierce for cup and cone bearings. The bearings used in these machines were crowded. Thus, though sliding friction between rollers and rings is low, there is a great deal between the rolling elements themselves. Today, crowded bearings are only used for applications working at low revs. For most cases, a means of separating the rolling elements is important. Cages eliminate sliding friction between rolling elements and are made for all sizes of bearings. Yet they cannot eliminate friction altogether, as there is now sliding between rolling elements and cage. This is one reason why modern bearings are by necessity among the most precisely mass-produced objects in the world: cages, rings, and the rolling elements themselves. 20 processes lie ahead of these: filing, honing, tumbling, polishing, washing, and all with the same object: the achievement of perfect roundness. Obviously, rolling elements must also be of uniform size. Here, each grading hole differs in diameter by 1/20,000th of an inch. Final inspection is human. Seemingly crude after such precise manufacture, but the experienced eye can spot imperfections which no machine can detect. Ultrasonic washing. Assembled bearings are immersed in a cleaning fluid which is then violently agitated by ultrasonic sound waves, causing dirt particles to fall away. From now on, for some types of bearings, conditions resemble those in an operating theatre. This clinical cleanliness is necessary, since here they are assembling small bearings as used in aviation instruments. The smallest speck of dust in them could cause utter disaster. The inner and outer rings are matched to a 20,000th of an inch. probably among the most precisely manufactured objects in the world, and accuracy comes in many sizes. This is just one manufacturer's range of rolling bearings. The single row, deep groove ball bearing is the commonest type. There is also the double row ball bearing, which is self-aligning. Cylindrical rollers for heavy radial loads. Needle rollers for assemblies in which space and weight are restricted. Spherical rollers, mounted double row, are again self-aligning, and they can take high radial and axial loads. And taper rollers, largely similar to spherical, are some of the many types in use. Hundreds and thousands of shapes and sizes, invisible, unnoticed, but keeping things turning by eliminating friction. Eliminating? Not completely, because if all friction were eliminated, the bearing would not roll. Consider the concept of a perfect frictionless, inelastic sphere, resting on a perfect plane with similar characteristics. The area of contact between sphere and plane is a dot. If horizontal force is applied, the sphere will slide. But the rolling elements are not perfect. This machine magnifies surface irregularities 10,000-fold. This hump represents a protuberance 1/40,000th of an inch high, but it is an irregularity. By gross exaggeration, a rolling bearing is like a rack and pinion, except that the two are not in mesh, since surface deformities do not coincide. Furthermore, most bearings work under load. If we look at a bearing under polarized light, we can see that the total load is taken by a small proportion of the rolling elements at a time. The theoretical area of contact between track and rolling element may be a dot. That the pressure area is larger in practice can be seen by the pressure waves. Here is a bearing whose ring has been specially coated with copper. A load is applied. This is a deep groove bearing. Ideal contact should therefore be a line. But the ball has been temporarily compressed out of roundness by the load, since steel is elastic, and an ellipse instead of a line has resulted. A rolling bearing resembles perhaps something like a vehicle track negotiating a corrugated surface. Therefore, the micro roughness and elastic compression of the steel are essential for rolling. But in practice, some sliding also remains, and it is to combat the effects of this that lubricants are introduced. First, there is sliding friction between elements and cage, as we said earlier, but this is sliding in a relatively lightly loaded area. More serious is slip in this area, called a Hertzian zone, and here is one factor which makes it inevitable. Let us look at a ball rolling on a groove. This diagram shows that true rolling without slip occurs only on the line CD. As we move away from this center section CD, the relative speed alters according to the diameter of the section, so that there is slipping at AB and EF. We can demonstrate the results of this clearly by the bands on this working ball and track. This, known as Heathcote slip, occurs also in the minute area of contact, the Hertzian zone, because of elastic deformation, where it is slight enough to be invisible, but nevertheless important. Most roller bearings need retaining lips to keep the rollers in position, and there is large sliding in this area. If an axial load is applied, the friction in this area can become seriously high. The chief function of a lubricant is to prevent metal-to-metal contact in all these zones. This is the largest slabbing mill in Britain, and the bearings on the rolls are subjected to ever-increasing loads. Metal-to-metal contact is avoided because in the loaded Hertzian areas, the film thickness of the lubricant is almost independent of load. That is according to the Elastohydrodynamic theory of lubrication, which we will attempt to explain non-mathematically. First, here is a rig showing ordinary hydrodynamic lubrication. It consists of a shaft and a plain bearing under load. Rotation of the shaft draws up oil from below into the loaded area where it is under greater pressure. Tubes show the actual pressure curve. The pressure is not great, perhaps 1,000 pounds per square inch. In hydrodynamic lubrication, film thickness is inversely proportional to load. This rig shows a rolling bearing rotating at 2,000 RPM, slowed down by high-speed photography. In rolling bearings, in load-bearing areas, pressure is great, perhaps 400,000 pounds per square inch. This is because the area is small. In elastohydrodynamic lubrication, film thickness is almost independent of load for two reasons. First, let us look at a roller stationary on a track. Diagrammatically, the pressure in Hertz dry contact areas may be shown thus. In motion, as we have seen under polarized light, the pressure areas are like this. But when in movement and lubricated, the whole pattern changes. This diagram illustrates the elastohydrodynamic lubrication theory. It shows a single roller when lubricant is introduced. The roller revolves in this direction and moves in space in this direction. The lubricant is drawn in here and leaves the contact zone here. With lubricant introduced, the load-bearing area increases due to the elastic deformation of the metal, and this deformation controls the shape and thickness of the lubricant film. The film thickness is almost independent of load in this area under high compression because the lubricant increases its viscosity immensely, behaving almost as if it were a solid film, perhaps 1/100,000th of an inch thick. And this film persists as long as the load exists, no matter how large. All 900 tons of this bridge pivot on these. No metal-to-metal contact because the lubricant film thickness is independent of load. In the GPO tower, people probably don't realize that they are not solidly connected to the ground. For most of the way they are, but there is a gap filled with lubricant, a gap a 50,000th of an inch high. The question now arises, which lubricants are suitable? In theory, anything with correct pressure viscosity characteristics for maintaining elastohydrodynamic lubrication. But in practice, so many other properties are required that the field is quite narrow. There is no universal lubricant. That is, one which prevents corrosion caused by damp and corrosion caused by vibration, has antioxidant properties, and can operate at extreme temperatures, can act as a coolant, and can seal itself in and dirt out. Various types of grease and oil have some, but not all of these properties. In this Rolls-Royce automatic gearbox, oil is used because it is the best lubricant for gears, and it is obviously simplest to use the same lubricant for the bearings. This application is not particularly critical. No extremes of temperature, no permanent heavy load, RPM seldom above 4,000. More important, the whole unit is enclosed in a casing which keeps out water and dirt. But here, oil is used both to lubricate the bearings and to cool them. A mile-long strip of metal at temperature is water-cooled and is coiled on the down coiler, which naturally absorbs some of the metal's heat. This heat must be conducted away again to prevent bearing failure. This calls for a thin oil, capable of being circulated in considerable bulk between cooling tanks and bearings. One big disadvantage of oil is that it cannot seal itself in. Certainly a seal can be fitted, but if it is close-fitting enough to keep the oil in completely, torque resistance increases. Oil can also be used in mist form, a most efficient method of lubricating, but complicated. Generally speaking, oil often gets where it's not wanted, and the food industry prefers not to use it. What is needed is something that keeps itself in and dirt out. And here, as in 90% of the world's rolling bearings, is the answer. In 1898, the editor of the Practical Engineer wrote, "A slight greasing of the rollers with petroleum jelly will do away with the necessity for oiling." True greases have only a superficial resemblance to petroleum jelly. Most consist of a metal combined with a fatty acid, to which is added an oil, generally a mineral oil, to the extent of about 90% of the total grease. Here is a bearing on a test rig. Normally, of course, the outer cover would be in place when running. Both covers are filled with grease, except for a small section in each, which is left empty. This is because the grease, with which the bearing is packed, is thrown outward immediately upon starting, and this grease takes up the space left for it in the cover. Under a stroboscope, we can see that in the early stages, the grease is violently agitated and movement occurs from the inner ring of the bearing across the cage. Whilst this is happening, intense shear, or fluid friction, causes a rise in temperature to a peak. We can also see that under this intense shear, the grease is losing its rigidity. We know that it is lubricating hydrodynamically where sliding is occurring in unloaded areas. But as we saw in the diagram, in the loaded Hertzian zones, it lubricates elastohydrodynamically, increasing its viscosity tremendously under load just for the instant of contact. As settled running conditions are achieved, this movement all but ceases, the grease forming an almost frictionless seal in the covers. The temperature falls and settles. In this case, both covers have been overfilled with grease. A transparent cover allows us to see what occurs in these circumstances. The stabilized conditions we have just witnessed collapse. There is not enough room in the housing to accommodate the surplus grease from the bearing, which is forced to retain it. The temperature stays up as the grease churns in the bearing. Grease is complex in nature and behavior, but simple to use. It can be packed into bearings and left for months, even under rigorous conditions. Electric motors like this are entombed in machines which regenerate fiber. The reagent is sulfuric acid. But the bearings come to no harm, for the grease seals itself in and the acid out. Simple to use, but complex in nature and behavior. Though its manufacture is fast changing from an art to a science, it is still impossible to forecast the behavior of grease in rolling bearings, save by empirical tests. Tests for load, temperature, and speed. The sound a bearing makes tells the technician as much as your chest tells a doctor. Failure. It could be a fault in the bearing itself, but with high temperature tests, the lubricant is often the chief suspect. Normal soap-based greases, even the most heat-resistant, cannot safely be used above 150 degrees centigrade. This is because such greases depend for rigidity on a network of fibers, here magnified 10,000 times. At critical temperatures, the relationship of these with the surrounding oil changes. But here is a clay-based grease under the same magnification, and this structure does not change. Here we are heating a metal soap-based grease on the left and a clay-based on the right. Clay-based greases are relatively new to industry and still being exhaustively tested, but possibly they will largely replace conventional greases within the next few years. In peculiarly severe conditions, they have done so already. This is a Swedish steel-making process, quicker than the traditional method and capable of producing as wide a range of steels. Oxygen is blown into the vessel, which raises the internal temperature in the furnace to 1660 degrees centigrade. Again, much heat is inevitably conducted to the bearings, yet they run on clay-based grease. But should a coolant be needed, no grease will be suitable, for it cannot be circulated to reduce temperature. Between them, grease and oil meet most modern-day requirements. This is the Victoria Line, 100 feet below Islington. Damp, mud, and heavy loads facing the mole. The very opposite here. No dirt, no heavy loads, simply precision. Gyro compasses are assembled in conditions even cleaner than our roller bearings. This is because their accuracy is vital. People's lives will depend upon them in the air. A marine gyro compass in a simulated gale greatly exceeding force 9. Every gyro undergoes this test, since it is in such conditions that it will be most needed. fuel elements containing uranium-235. This is the pile cap at Sizewell Atomic Power Station, with the fueling machine moving into position. Inside this piece of equipment, bearings are needed for the mechanism which lifts used radioactive elements out of the pile. Most bearing lubricants were found to be useless under such intense radioactive conditions. The grease in the cover changes, in this case becoming liquid. After much development work, this problem has been overcome, and a grease which will maintain its consistency under intense radioactivity has been produced. Today, some 7% of Britain's electric power is nuclear. Industry as a whole makes increasing demands on bearings, but the aviation industry makes the most severe. This bearing is in the heart of the Olympus engine which powers the Vulcan, and will also be used on the Concorde. The combination of high thrust, RPM, and temperature makes what is probably the biggest demand on a rolling bearing in history. Wonderful, supernatural, a pivot in highest perfection. Leonardo exaggerated, but this is the limited perfection which we have so far achieved.